So now I just want to pause here and talk a little bit about average stresses. Okay, so what we've been doing so far is if we had some kind of bar, in this case it's going to be rectangular, and it has a force on it, some force P, and it has some area. I'm going to call that A1, and I have some hole in it here. If I wanted to know what the stress is at the end of that bar, you would say, okay, well, it's P over A1, all right? That would be the average stress. So now let's look what happens if we take a cut. So let's take a cut right here. I'll draw this stuff again. So we got this end, we got this end over here. We still have that right there. The hole is right about there. We still have P going that way. And now we have some internal stress. So that's going to be sigma. And we would say the average stress would be P over A1. And in that case, yeah, it's actually a pretty good approximation. That's what we've been doing so far, and that's certainly okay. The next question is, what happens if I take a cut a little bit closer to the hole, or right on the hole? So that's what I'm going to show next. Here's a cut right on the hole, and so that cut might look something like that. And we'd still have our force on here going that way, P, and we'd still have some stress on this side. And if I say that this area here, I call that A2, you might be tempted to say, okay, well, I'm just going to have an average stress. And that average stress is going to be sigma is equal to P over A2. And unfortunately, that is not a very good assumption. We have this disturbance of the hole. And as it turns out, that disturbance causes a quite complicated stress picture. So right around that hole, we end up having a non-uniform stress. And so what this ends up looking like, if I can draw this picture a little bit better, what the stress actually looks like here, we have P going that way. What we'll end up having is the stress is going to increase next to the hole. So this is a stress concentration, and this is why you have to be careful when you have bolt holes or something like that, that you don't exceed the kind of the yield stress or the ultimate stress of the material. This stress picture is important when you're talking about strength, right? If the material has a certain stress at which it fails, then this non-uniformity in stress matters if you're thinking about its strength of this whole bar here that we're looking at. So that's one of our two observations. The second one, there we go. The second one is that if I just have a bar and it has a hole in it, and I pull with some force P, and I look at the elongation of that bar, as long as there's not a lot of holes, as long as there's just this one hole at sort of location and there's quite a bit of bar on both sides, we don't really have to worry about the hole. So the non-uniformity of stresses or deformations, the non-uniformity dies out as you get further away from a disruption. And in this case, that would be our hole. Could also be a discontinuity, it could be some end condition, but as you get further away from that disruption, the non-uniformity in stresses die out, and it's about 1 member depth away. So for our little rod here, that would be 1 depth of our rod. The other thing that you can notice is that the average stress is okay for deflection. So that would be thinking about the deformation of our total rod from end to end. But the strength depends on the max stress. So that's getting back to our conversation we were having over here. That if you were worried about this thing failing, you would need to think about this stress concentration near the hole. And this concept that we're talking about here is St. Venant's principle. All right. And it is attributed to Adhemer Jean-Claude Barre de St. Venant. It's kind of a mouthful, but that's back in 1855. So, while you can't rely on the average stress always giving you a clear picture of the strength of a member, you can assume the average stress will tell you something about the deflections. And if you're concerned about figuring out the stress at some point that's greater than 1 member depth away from a disturbance or a disruption, then the average stress is going to be pretty close. And that's going to help us all the time in engineering. Makes things easy for us, not having to worry about these disruptions a lot of the time. So the other point I wanted to make about average stresses is that they can also ignore other types of stresses. So that would be bending, or maybe residual stresses from heating. So if we have a nondescript member here, and we apply stresses that look like this, so here would be some compression, this would be some tension. The sigma average would actually be 0. So in our just 1D sense, there would be no stress that would be acting on that member. But as you can see, we have tension, we have compression, we have a potential for failure. The other thing that can happen is thinking about the same nondescript member, but if it's an interesting shape, an eye girder or something like that, it'll cool at a different rate based on the thicknesses of the different parts. And what can happen is that you'll end up getting a stress picture that looks something like that. So you'll have compression in the middle, you'll have tension on the outside, and again, sigma average can be 0. But if there's a critical stress that causes failure or causes some kind of behavior you don't want, these initial stresses are going to be important to consider. So average stresses are good for a lot of things, but you also can't forget about some of these discontinuities, the stress risers that they create, and you also can't forget about some of these other sources of stresses that might not be included in your simplistic analysis.